Okay, thank you. Yeah, my name is Chang from Penn State, and I know this is a theory winter school, and you will see less and the simplest equations in my slides. And my students have been here for many times. This is my first time to be the magnetic lab. And today in my talk, I will introduce this kind of the synthesis method, the MBE. And in this morning, we have two talks about the quantum Hall effect. For quantum Hall effect, for the sample like gallium arsenide, and we're still using this kind of MBE to get the highest quality of the samples. Today, I will focus on this kind of using MBE to synthesize this kind of the quantum material film heterostructure and also superlattice. I will focus on two topics. The two zero resistance phenomena is the quantum anomalous Hall effect. We know quantum Hall effect already, and quantum anomalous Hall effect is just the quantum Hall effect at zero magnetic field. And the second half of my talk, I will focus on this kind of the interfacial superconductivity if we use MBE to grow to this kind of the non-superconducting material, and we get the superconductivity. We call it interfacial superconductors. And here, this kind of motivation is we want to let the quantum anomalous Hall to join the superconductivity game to realize this kind of the Morana physics in the kinetic matter field. So here, let me briefly introduce this kind of the molecular beam epitaxy. And this is the MBE growth chamber. Usually we're using several kinds of this kind of pump to get this kind of really high vacuum is 10 to minus 10 or 10 to minus 11, this kind of millibar, just like in this room, there is 1 or 2 atoms. And here, this is the manipulator. We usually put the sample here, and we have this kind of the different sources. And we heat these kind of sources to evaporate the sources to get this kind of the thin film heterostructures and the superlattice. That's because this kind of in the MBE chamber, is really high vacuum. So the film and the samples we grew here usually with the really high purity. That's also the reason we could realize this kind of the quantum phenomena in the MBE growing samples. This is the schematic for the MBE growth of the bismuth selenide, and the bismuth selenide is a typical of the 3D topological insulator. And here later we will base on this kind of 3D topological insulator for the realization of the quantum anomalous Hall insulators. And in this kind of the MBE chamber, we can see that the bismuth is element, single atom element, and for selenium is selenium 2 and selenium 4, this kind of molecular. And we base on this kind of the chambers, we could get this kind of really high purity bismuth 2 selenium 3 films. And here is the MBE facility in my group at Penn State, and we have this kind of the 3 MBE chamber. And this is the MBE chamber. This is the real picture of the MBE chambers. And this MBE chamber is dedicated for the growth of the magnetically doped topological insulator. Later, I will show you why and how we're using the magnetically doped topological insulator for the realization of the quantum anomalous Hall insulators. And this is the MBE chamber 2, and we can grow the sample and check the band structure, electronic band structure, using the RPAS. The RPAS here, it just be considered as a gross eye to characterize the sample quality. And here is we have a MBE chambers. For this, the chamber is dedicated for the growth of the quantum anomalous Hall and the superconductor heterostructures. In the second half of my talk, I will focus on this. And when we grow this kind of sample, we can, without breaking ultra high vacuum, we can do this kind of STM studies to check the physical property of the quantum anomalous Hall or superconductor or topological insulator superconductor heterostructures. So here we know that in the solid state physics or in kinetic matter, there are two phenomena with zero resistance. One is the superconductivity. This is the original data in the mercury is 4.2 Kelvin. The TC is 4.2 Kelvin. And the second phenomena we have here two talks about the quantum Hall effect is quantum Hall insulators. If we put this kind of 2D electron gas in the strong magnetic field, and there the electrons can only pass through this kind of edge and forms this kind of the quantum Hall insulators. And this kind of quantum Hall insulators is usually realized in the 2D electron gas under the strong or high magnetic field. And in this talk, I will show this kind of the two phenomena and why this kind of the unique kind of the quantum Hall insulators, we call it quantum anomalous Hall insulators. As I told you, it does a quantum Hall insulators under zero magnetic field. And the second half, I will introduce the interfacial superconductors. And here it does how we use MBE to fabricate, to synthesize to non-superconducting material. And later we realize the interfacial superconductivities. So here is the outline of my talk. And first, I will briefly introduce the quantum anomalous Hall effect. And later, I will show you, the 10 years ago, how I realized using MBA to grow the magnetically doped topological insulator film to realize the quantum anomalous Hall effects. For the first time, and in 2017, I joined Penn State, and over the past almost 10 years, and we have continued to do these kind of directions and have done a lot of works in this kind of the quantum anomalous Hall effects in the chromium-doped topological insulator multilayers. And in the second half of my talk, I will focus on with the motivation that for the realization of the Majorana physics in the solid state system, we try to using this kind of the MBE to grow the quantum anomalous Hall and entire heterostructures. Both are non-superconducting materials. If we stack them together, we could realize the interface-induced superconductivity. And at the end of my talk, I will briefly introduce how to prove or how to detect the Majorana physics in this kind of the quantum anomalous Hall and entire heterostructures. So in the first two talks in the morning, we already knows what is Hall effect. So we knows that in 1879, Adam Hall is a graduate student from Johns Hopkins and first discovered the Hall effect. And here is just the Hall effect is for metallic or semiconducting materials. If we put this kind of the magnetic field, perpendicular magnetic field, the carriers will be pushed towards to the two sides of the sample and forms a transverse voltage. We call it Hall voltage, and this phenomena we call it Hall effect. And this is the original data Edwin Hall measured on the gold leaf. We know that for the Hall effect now is still widely used in the kinetic matter field. For example, if we synthesize some single crystal or some crystals, that we usually using the first measurement is the Hall measurement to check the carrier type, carrier mobility, and also carrier densities. So here we will ask one question: if we further, if we apply this kind of really high magnetic field in this kind of the 2D, this kind of the semiconducting or metallic samples, what will happen? So that is just the Hall effect. And we see this kind of the similar image in the first two talks. And we know that you see that at high magnetic field, the Hall resistance is quantized and the longitudinal resistance is vanishing, is close to zero. And for the quantum Hall effect, we know that already in the first two talks is first discovered by Van Clichy in 1980s. And we know that for the quantum Hall effect is usually observed in 2D electron gas at low temperature under high magnetic field. So here we will ask one question: can we realize quantum Hall effect without the need of the external magnetic field? So the answer is yes. So that kind of the zero field quantum Hall effect is called the quantum anomalous Hall effect. So here is the Hall family. There are three basic members: Hall effect, anomalous Hall effect, and spin Hall effect. And their quantized version, we call it quantum Hall effect, quantum anomalous Hall effect, and quantum spin Hall effect. So today, in the first half of my talk, I will show you the how and why we realize this kind of quantum anomalous Hall effect in the magnetically doped topological insulators. In the quantum anomalous Hall effect at zero magnetic field, we can see that the Hall resistance is quantized and the longitudinal resistance is vanishing. And at zero field, we call this is quantum anomalous Hall insulators. When the magnetization down, the eddy state goes this way. When the magnetization up, the eddy state goes the opposite way. So the chirality of the eddy state depends on the magnetization of this kind of the quantum anomalous Hall samples. And we see that at zero magnetic field in quantum anomalous Hall insulators, the Hall resistance is quantized at 25.8 kilo ohm, and the longitudinal resistance is vanishing, is close to zero. So here, why the quantum anomalous Hall insulators is interesting is just because there is, we call it chiral eddy channels, and these chiral eddy channels is being polarized and also ballistic. And we notice that in the conventional metal or conductors or semiconductors, for the carriers in these kind of the conventional metals, there are four possibilities: spin up, spin down, right mover, and left mover. So the impurity in these kind of the conventional conductors will backscatter the right mover to the left mover and give rise to the electrical resistance. So these kind of the carriers or electrons in these kind of the conventional conductors, like this kind of the car and buses in a traffic jam, that's also the reason we could have this kind of electrical resistance in the conventional conductors. So in the quantum anomalous Hall insulators, for the carriers, there is only one possibility, is we call it this kind of the spin up dispensionless chiral eddy state. So the electron or the carriers in this kind of the quantum anomalous Hall insulators, just like the traffic in this kind of highway. So you know that just because of this kind of chiral eddy state in the quantum anomalous Hall insulators, the quantum anomalous Hall is really interesting system in the kinetic matter physics, and the quantum anomalous Hall also provide a platform for the development of this kind of the energy efficient spintronics and electronics. And also, there are a lot of proposals about this kind of the topological quantum computing based on the quantum anomalous Hall's chiral eddy channels. So I like this kind of quantum Hall and fractional quantum Hall. We hear this kind of the quantum Hall and quantum fractional quantum Hall in the first two talks. I like the quantum Hall and the fractional quantum Hall. Both start from this kind of experiments, and later theorists try to interpret quantum Hall and fractional quantum Hall. For the quantum anomalous Hall, is actually first starts from the theoretical prediction. In 1988, Duncan Haldane proposed this kind of the quantum Hall without lambda level. We call it quantum anomalous Hall in this kind of one layer of the carbon atom. One layer of carbon atom. Today we usually call it graphene. And in this kind of Haldane's model, he considered this kind of the nearest hopping and second nearest neighbor hopping in his calculation. If the second nearest neighbor hopping T2 equals to 0, we know that at the Brillouin zones there are this kind of the gapless surface state. So this is just the band structures of the monolayer graphene system. And if we consider the phase of the second nearest neighbor hopping, and the gap will open at Dirac point, And if based on Haldan's model is a toy model, if we could tune the chemical potential into this small gap, in principle or theoretically, we could realize the quantum Hall effect without the need of the external magnetic field. But you know that there is a problem here is graphene is formed by carbon. Carbon is a light element. So based on this Haldan's model, it's really difficult to break the time reversal symmetry by this kind of magnetic doping in this kind of the system. So here, we notice that this is the Haldan's model. So in other words, for the quantum anomalous Hall effect can also be considered as the quantized version of the anomalous Hall effect. We know anomalous Hall effect is just the Hall effect in the magnetic materials. So there are a lot of magnetic materials. We have anomalous Hall effect. If we could quantize the anomalous Hall effect in the ferromagnetic materials, we can also realize the quantum anomalous Hall effect. For the anomalous Hall effect in the ferromagnetic material, for the intrinsic anomalous Hall effect, what is intrinsic? It just because of the band, this kind of electronic band structures. So the first recognized by the Kemplers and Latinger in the 1954, and we know that in the 1980s, when the Barry language is established, so we can, in principle, to calculate the Hall conductance by the integral of the Barry curvature in the first Brane zone, and the integral of the Barry curvature is 2 pi times c. C is an integer number. So if we put this equation here, this might be the only equation in my talk. And if we put it here, we can get a really simple equation. Is sigma xy Hall conductance is equal to E squared over H times C. C is, we usually call it a chain number. And from this equation, we can easily to get the two conditions for the realization of the quantum anomalous Hall effect. So if sigma xy is quantized, C must be non-zero. So must be non-zero. Now we call it there is inverted band structure. We also call it the material is topological material. So the second condition is ferromagnetic material. The material is ferromagnetic, and also with this kind of inverted band structure, based on the theoretical prediction, we may realize the quantum anomalous Hall effect. So this is the what based on this kind of the equation we get. If we could find one material satisfy these two conditions, we may realize the quantum anomalous Hall effects. So, but we know that in 2006, so the theoretical prediction and also later just the experimental realization of the topological insulator makes this kind of the realization of the quantum anomalous Hall become possible, because in topological insulator, the inverted band structure is already realized. So here, let me briefly introduce the topological insulators. So what is topological insulator? So I think most of the audience is familiar with the topological insulator. So here I give a really brief picture. So this is a banding insulator. This is conduction band and this valence band. We usually call it, this is banding insulator or regular insulator. So if the strong spin orbit coupling is introduced into this kind of the banding insulator, the conduction band and the valence band will be inverted, and a gap will be opened between the conduction band and valence band, and a linear dispersion, this kind of the surface state will be formed between the conduction band and the valence band. So this surface state, we usually call it Dirac surface state. And we know that for the topological insulator can be clarified or classed into this kind of the 2D topological insulator. Sometimes we also call it quantum spin Hall insulator, and 3D topological insulators. For the 2D topological insulator was first theoretically predicted in the mercury telluride and later realized by Lawrence Mollingham's group in Germany in this kind of mercury telluride quantum wells, and later in this kind of the indium arsenide and gallium antimonide quantum wells also realized this kind of the 2D topological insulator phase. And today in my talk, I will focus on this kind of 3D topological insulator. for the 3D topological insulator was first predicted by Liang and Penn in this kind of bismuth antimony compound, and later realized by the Zahid Hassan's group at Princeton. But for this system, there are multiple this kind of Dirac point, and it's pretty complicated. And in 2009, in this kind of the Zhongfang's group at the Institute of Physics of China predicted this kind of the bismuth selenide family with this single Dirac core in the first in 1 billion zone, and later realized by the Zahid Hassan and also the X group at Stanford University. So now we have the topological insulator. That's based on what I told you. We have two simple conditions: inverted band structure and ferromagnetic material. So now we have inverted band structure. In topological insulator, that's because we call it topological. There is already inverted band structure. So based on this kind of if we could introduce the ferromagnetic order into topological insulator, based on Howland's theory or based on what I told you, we may realize the quantum anomalous for insulators. So here is the logic, or here is the theory why we're using this kind of topological insulator for the realization of the quantum anomalous for insulators. As I told you, that this is the topological insulator, this is the Dirac surface state, and the Dirac surface state is protected by time reversal symmetry. If we could introduce the ferromagnetic order into this kind of topological insulator, this ferromagnetic order will break the time reversal symmetry in topological insulators and form a gap at the Dirac point. So this gap is not the bulk gap. We usually call this small gap is magnetic exchange gap, is a gap within the bulk gap. The bulk gap is here, so this is magnetic exchange gap. So for the magnetic exchange gap, is usually really small, it's 1 or 2 millieV, this kind of energy level. And based on this kind of the theory, if we could tune the chemical potential into this really small magnetic exchange gap, we may realize the quantum anomalous for insulators. So this is the theoretical picture why we use this kind of the topological insulator for the realization of the quantum anomalous for insulators. I'm an experimentalist. We need to convert this kind of the theoretical picture into experimental steps. And here, using one statement to describe this kind of how we can realize quantum anomalous Hall in the real materials is we employ NBE to grow this kind of if we could grow an insulating magnetic topological insulator, the film, we will realize, we have topological, we have ferromagnetic order. The insulating means you tune the chemical potential into the magnetic exchange gap. So this is the language I can understand. So if we could use NBE to grow an insulating magnetic topological insulator, the film, we may realize the quantum anomalous Hall. So that's but during this kind of the synthesis, we need to keep this kind of the four conditions. How to introduce this kind of the ferromagnetic orders into the topological insulator, the film, and how to realize the insulating property of the magnetic doped insulators. So when you dope this kind of the transition metal into this kind of the topological insulators, the band topology unchanged. We need to keep the topological property of the materials. If you do something into topological insulator, the non-trivial property disappears. That's not good. We need to keep the inverted band structures. And we also, there should, in this kind of film, there is no this kind of magnetic element clusters. And also, we need to realize insulating magnetic topological insulator films. So no extra charge carriers. If you do something in your topological insulator, you need to keep this kind of topological insulator still insulating. And here is, we know the quantum anomalous Hall is an insulating phenomenon. So that means this kind of the ferromagnetic order must be still exist when the sample become an insulator. So actually, this is a pretty strict this kind of requirement. We know that in the diluted ferromagnetic insulators, so for ferromagnetism is always realized in the p-doped this kind of samples. With Hall carriers, you will get ferromagnetism. With the electron carriers, no ferromagnetism. Without these kind of carriers, you also have no ferromagnetism. So here is in this kind of magnetically doped topological insulator films, the ferromagnetic order must be carrier independent. So here, in my PD, I spent almost 3 or 4 years, almost 4 years to grow this kind of the chromium-doped bismuth antimer telluride samples. So here, why we choose this kind of the samples, we know that bismuth telluride is N-type, antimer telluride is P-type, so we mix them together. So this is just to get insulating phenomena. For chromium dope, it's just to get the ferromagnetic property to satisfy the three conditions we can say: insulating, ferromagnetic, and topological. So in this kind of the 4-element materials, we try different chromium doping level, we try different bismuth antimer ratio to make the sample insulating, and we try different thickness of the samples, and try different protection layer. We grow the sample in ambient chamber. We need to take them for the essential transport environment. So we need the different protection layer, and we try different this kind of Hall bar, these kind of configurations. So here is the Hall resistance as a function of the time. We can say that on this kind of October 9th, 2012, we were the first to see this kind of the quantum anomalous Hall effect. We can call it quantum Hall effect without the need of external magnetic field. You can see that. So this is also forms a plateau in the time of this kind of I spent about 3 years to realize the quantum anomalous Hall effects in the magnetically doped topological insulator thin film. So here is the sample. We finally, the perfect data, we realize this kind of the quantum anomalous Hall effect is a 5 quintuple layer. Quintuple layer is just 1 quintuple layer is 1 nanometer. So the sample thickness is 5 nanometer, chromium doped bismuth antimony telluride films. So here at charge neutral point, we can see that the Hall resistance is quantized at E square over H over E square, and the longitudinal resistance is approaching to 0. And here we can, if we plot the zero field Hall resistance and the longitudinal resistance as a function of gate voltage, we can see at charge neutral point, the Hall resistance is quantized, exhibit this kind of the plateau at the charge neutral point, and the longitudinal resistance is approaching to 0. So this kind of the phenomena marks the first realization of the quantum Hall effect without the need of the external magnetic field. So this work is also featured in the 2016 Nobel Physics Prize to demonstrate the contribution from Duncan Haldane for the prediction of the quantum anomalous Hall effects. So here, as I told you, why the quantum anomalous Hall effect is interesting is because of the this pencilless chiral edge state. So here, this is the C equal to 1 quantum anomalous Hall. So in the previous slides, so this is the quantized at E square over H. So we call it, this is the chain number is equal to 1. There is only 1 chiral edge channels in the quantum anomalous Hall insulators. So here, if we just think about, can we realize this kind of high chain number, with multiple chiral edge channels in the quantum anomalous Hall insulators? For example, in the C equal to 1 quantum anomalous Hall insulators, the resistance, the chiral edge channel is this pencilless, but the resistance is still formed at the contact areas. So from the contact to the chiral edge channels, just like you drive a car from the downtown to the highway, is still, if there is only one lane, it still takes you a lot of time. But here, if we have multiple links, we can greatly reduce the contact resistance in this kind of the quantum anomalous Hall insulators. So here it does C equal to 3, this kind of quantum anomalous Hall effects. We have 3 these kind of chiral eddy channels. Can we realize the high chain number quantum anomalous Hall insulators? So here is the work we did 5 years ago. We call it quantum anomalous Hall insulators with multiple these kind of chiral eddy channels. So here is the C equals 3 quantum anomalous Hall insulators. This is the logo, this kind of schematic. You know, at that time there is Cui-Zu. I play logo with my old son a lot. So I learned from that kind of the logo structures. So you know that we can grow the pretty good C equal to 1 quantum anomalous Hall insulators. Can we stack them together? We find a glue to stack this kind of the C equal to 1 quantum anomalous Hall insulators and realize the high chain number of quantum anomalous Hall effects. So here, this kind of glue should be a normal insulator layer, and from the MBE synthesis point of view, so this normal insulator layer should share the same lattice structure and lattice constant with this kind of the C equal to 1 quantum anomalous Hall layers. In other words, is chromium doped bismuth antimer telluride here. And here, you know, over the past, at that time is 7 to 8 years, it's really difficult to find these kind of the normal insulators. So here we take really smart ideas. You know that if chromium is a light element and bismuth antimony is a heavy element, if we heavily dope chromium into this kind of bismuth antimony telluride, we could greatly reduce the spin orbit coupling and drive this layer become a normal insulator. But this kind of normal insulator shares the similar lattice constant or lattice structures with the undoped this kind of film. So here is we give this kind of interlayer structure. This is the TEM image. We can see here this is 3 quintuple layer, heavily chromium doped bismuth antimer telluride, and here is 4 quintuple layer undoped bismuth antimer telluride. We can see this kind of perfect, this kind of the multi-layer structures. And for this kind of structures, we grow this kind of C equal to 1, this is tri-layer structure, pentalayer structure, 7-layer structure to this kind of these 11-layer structures. We perform this kind of the dilution measurement. We can see that for tri-layer structure, the Hall resistance is H over E squared, pentalayer H over 2E squared, to this kind of H over 3E squared to H over 5E squares. And now in MagLab, we can get C equal to 30, C equal to 20, these kind of really nice samples. And here we can see that for all these samples, the longitudinal resistance is approaching to 0. So this kind of the data demonstrated the realization of the high chain number quantum anomalous Hall effects in the magnetic TI, these kind of multi-layer structures. And the chain numbers is just depends on the gray color, how many gray colors in your this kind of multi-layer structures. You know, this is the undoped TI layers. If you have 5 layers of the undoped TI layers, the chain number is equal to 5. So here actually there is based on this kind of our understanding, actually we could tune the chain numbers by several these kind of parameters. So here we take this kind of painter layer as an example. We grow this kind of samples. So here, if we could change in this layer, in the middle layer, we change the chromium doping level. As I told you, if chromium doping level is low, it's not trivial. It's high, it's trivial. So here, let's see, if the chromium doping level is low, so this is non-trivial, this is non-trivial, this is also non-trivial. The non-trivial layer will become one non-trivial layer, so you have only 2 surface states. The 2 surface states, each one contributes 1/2 Hall conductance. So this should be C equal to 1 quantum anomalous Hall. When you increase the chromium doping level, this becomes trivial, this is non-trivial, this is non-trivial, so you will have 4 this kind of diagonal surface state. So 4 times 1/2 is just 2E squared over H. So this is here is our experimental results. We can see that when the chromium doping level is 0.13 and 0.15, the sample is quantized at h/e². So consistent with our understanding. So here is when the chromium doping level is 0.24 and 0.35, the doping the Hall resistance is quantized at h/2e². So here is the theoretical pictures. Here is a schematic. With increasing the chromium doping level, we can tune the C = 1 quantum norms for insulator to become a C = 2 quantum norms for insulators. And this is tune this kind of the chromium doping level. And we can also tune the chain number. If we fix the doping level here, we can tune this kind of chain numbers by tune the thickness of the middle layer. For example, when the thickness is thinner, is C = 1. When the thickness is thinner, become a C = 2. So here, over the past almost 10 years, my students spend a lot of time in improving this kind of the synthesis of the quantum norms for insulator samples. Now we can grow pretty good the quantum norms for insulators. And here we grow this kind of, we always know that the quantum norms score is a 2D phenomenon, but here we grow really thick samples. So here is 106 nanometers. Now we can grow 200 or 300 nanometers, or also realize pretty good this kind of the quantum norms score effects. So here we can see this 106. This is exactly 100 years. At first I don't believe my student. I asked them to count it exactly 100 quintuple year here. So that means our growth is pretty high precise. And this is the 106 nanometer is 10 times the current this kind of world record. And we can say if we do the transport measurement, we can still see the pretty good quantum norm score effects. And that from these slides, what we learned is, if you could make this kind of the middle layer insulating, we may realize quantum norm score effects in pretty thin this kind of the magnetically doped sandwich structures. In other words, is if I don't tell you the thickness of the sample, that's based on the transport data. It's difficult to distinguish this data is from the thinner sample or thinner samples. So, and more recently, we still using the MBE to fabricate this kind of magnetic TI sandwich structure with the different doping. And the top layer we doping the vanadium, and the bottom layer we dope the chromium. That's because of two different doping. There are two different this kind of magnetic anisotropy. So they are the top layer and the bottom layer have different this kind of the QAHE field. So we know that for vanadium is the HC is around 1 Tesla, and chromium is around 0.1 Tesla. So when we apply in-plane magnetic field, vanadium will become chromium will become in-plane, but vanadium still keeps out-of-plane. So here we can see our data here. So when you apply the in-plane magnetic field, we realize this kind of the C = 1/2, this kind of robust quantized plateau, and this state corresponds to the theoretical prediction. We call it the C = 1/2 parity anomaly state. So the paper it just published last week. And here now we have the quantum norm score insulators, and I already told you quantum norm score insulator is interesting. There is one this kind of application of the quantum norm score insulator is, okay, there are a lot of theory to predict Majorana physics in the quantum norm score and the superconductor heterostructures. We know that why in the solid, the Majorana is a name from particle physics, and why in solid state this kind of field, we always use this kind of the superconductors for the realization of Majoranas. So here I give these kind of really simple pictures. So this an electron in this kind of Cooper pair is equal to a hole in the Cooper pair C. If you have a Cooper pair C, an electron is just equal to a whole. So this is satisfy the definition of the Marianas. So here is in this kind of the quantum anomalous Hall and the superconductor heterostructures, there are two kinds of Mariana based on theoretical prediction. One we call it Mariana zero mode, is bounded to this kind of the vortex or this kind of the samples. You know, if you have a external magnetic field, there is vortex, there is one kind of this Mariana, we call it Mariana zero modes. And in quantum anomalous Hall and superconductors, there is another unique kind of the Marianas, we call it chiral Mariana. And this chiral Mariana can propagate along the 1D edge of the samples. And this kind of the chiral Mariana can only be realized in the quantum anomalous Hall and the superconductor heterostructures. So I'm an experimentalist, so we need to realize, we need to synthesize this kind of the quantum anomalous Hall and the superconductor heterostructures. You know, over the past 10 years, here is the first work we did is we using sputter to sputter this kind of nanobeam on top of the quantum anomalous Hall insulators. So here is based on our experiment, we just demonstrated. Okay, you know you using sputter this kind of the nanobeam on top of the quantum anomalous Hall insulator. This nanobeam is really thin, is 100 nanometer thick, is polycrystal, and this kind of the nanobeam layer just short the sample. There is no Mariana physics based on this kind of the electrical transport measurement. And you know, I'm an MBE grower. I really want to grow this kind of the using MBE to grow this kind of quantum anomalous Hall and the superconductor layer within a chamber with a really sharp interface. You know, the sample quality for me, you know, for most of the experimentalists is really important. Is if we could grow this kind of the magnetically TI and nanobeam, this kind of heterostructure within one MBE chamber with the sharp interface, that's the best quality of the quantum anomalous Hall and the superconductor heterostructures for the exploration of Mariana physics. But we know that for topological insulator is hexagonal lattice structures. From the traditional MBE knowledge, we need a superconductor also with the hexagonal lattice. You know, if we exclude the single element superconductors, there are only 2 or 3 superconductors with hexagonal lattice. So the first superconductor we try is nanobeam selenide, is a hexagonal heterostructures. And we grow the monolayer nanobeam selenide. The TC is around 3 Kelvin. That's reasonable. It's comparable to the exfoliate monolayer, this kind of the nanobeam selenide. But we found that if you grow the bismuth selenide on top of nanobeam selenide, the superconductivity will be greatly reduced. And for sometimes it's completely killed. So this is not like the theorist prediction. You know, theorists, if you put a quantum anomalous Hall on top of superconductor, the superconductor can survive forever. But in experiment, if you have a superconductor layer, you put magnetic TI or TI on top, you will kill or suppress the superconductors. It's not like what we think about. So here, you know, we need to have a quantum anomalous Hall and a superconductor layer with robust superconductivities. So this is just what we did what we did over the past 3 or 4 years. Here, the system we grow is we really want the quantum anomalous Hall become one component of the superconductivity. If become one component, so you know the superconductivity will always survive. So here is the system we grow is topological insulator, bismuth antimer telluride, and antelluride heterostructures. We know that for bismuth antimer telluride, as I just told you, is topological insulator, is non-superconducting, and for antelluride is one element of this kind of the iron chalcogonide, but it's antiferromagnetic, is also non-superconducting. So here, bismuth antimer telluride is hexagonal, and antelluride is cubic. Based on just I introduced the traditional MBE knowledge, this is not good. But in our experiment, we always see this kind of really sharp interface. Later, I will show you why. So here we can see from this TEM image, we can get this kind of the 8 quintuple layer bismuth antimer telluride and iron telluride film. So here is quintuple layer structure, 5 layer structures, and here is tri-layer structures. For iron telluride is tri-layer structures. So we perform this kind of the transport study for the iron telluride itself. So we can see that at 54 Kelvin, there is a hump. Usually this hump is associated to the phase transition from paramagnetism to the antiferromagnetic transitions. So this we call it near temperature at 54 Kelvin. If we deposit 8 quintuple layer bismuth telluride on top and antimer telluride on top, there is a sharp this kind of the superconducting phase transition appears. So here we can see that for 8 quintuple layer bismuth telluride and 50 unit cell iron telluride, the TC is around 14.2 Kelvin. And for antimer telluride and iron telluride heterostructures, the TC is around 12.5 Kelvin. So here we also perform this kind of STM studies on this kind of the bismuth antimer telluride and iron telluride samples. So here is 1 quintuple layer bismuth telluride and 40 unit cell iron telluride. We see this kind of wave-like features, and this is induced by the it's a more structures induced by the tellurium atom in the top this kind of bismuth antimer telluride, and the bottom this kind of tellurium in the iron telluride layers. And here we can see this is the lattice peak, and this is the more induced this kind of the structures here. And we do this kind of the STM measurement, we see a really good this kind of the U-shaped gap, and the superconducting gap is around 2 millieV, and the U-shaped gap is first realized in this system. And here we do this kind of the high magnetic field measurement. Here, high magnetic field is pulse. This induced high magnetic field is is done at Los Alamos. And here we can see that for bismuth telluride and telluride, when you apply this kind of the high magnetic field and change this kind of theta, theta is the normal direction and a magnetic field direction, we can see that there is, almost identical behaviors with different theta. So that means this kind of the superconductivity in this system is isotopic, and in antimer telluride is also isotopic. So this is, at first I thought this is interesting, and finally I think this is a general, this kind of property in the iron-based superconductors. But for here, we can see that the HC2 is pretty huge, is 40 Tesla for the this kind of heterostructures, for these two heterostructures. I'm an experimentalist from a really naive point of view. Okay, you have a large HC2. If you change this kind of the bismuth antimer telluride, replace this kind of bismuth antimer telluride by the chromium-doped bismuth antimer telluride, so the superconductivity may still survive since you have large HC2 here. So with this board gas, we do this kind of the NBE growth for this kind of the quantum anomalous hole. Quantum anomalous hole, as I just showed you, is chromium-doped bismuth antimer telluride. So for chromium-doped bismuth antimer telluride and iron telluride heterostructures, and this is ferromagnetic and definitely non-superconducting, and iron telluride antiferromagnetic, non-superconducting, two magnetic material. Let's stack them together using MBA to see if the interfacial superconductivity still survive. So here we grow this kind of 8 quintuple layer chromium-doped bismuth antimer telluride and 50 unit cell iron telluride. We can see here the interface is really good, and later I will show you why it is good. And here we can see this kind of the red color here is based on this kind of the EDS, this kind of measurement. There is chromium doping here, and we do the transport, we can see the superconductivity still survive in this kind of the two magnetic material formed these kind of heterostructures. So here the TC onset is 12.4 Kelvin. We can see the superconductivity survive in the in this kind of the magnetic heterostructures. So here, as in my first half of the talk, I already told you chromium-doped bismuth antimer telluride we usually call it quantum anomalous Hall insulators. So here we use 8 quintuple layer chromium doped bismuth antimaterite. If we grow it, it shows the pretty good quantum anomalous Hall effects. In this, the top layer of here. So here is the 8 quintuple layer chromium doped bismuth antimaterite. So here, based on the traditional MBE knowledge, usually, for MBE grower or for this kind of a single crystal grower, we always think about if you want to form a heterostructure, the bottom layer and the top layer need shares the same lattice structures. If you want to grow cubic material, must be on cubic material. Hexagonal material must be on this kind of hexagonal, this kind of substrate. But here, the bottom layer antaride is a cubic material, and top layer is hexagonal material. Why? You can still realize the really sharp interface. So here is the reasons. So we know that for chromium-doped bismuth antimaterite, the lattice constant is around 4.26 to 4.38. For the antarite is 3.67. That there is satisfy these kind of equations. If you satisfy these equations, you can actually perfect stack this kind of the hexagonal lattice on top of the cubic lattice structures. And that's also can explain in our MBE growth, the read pattern is always sharp. And in TM image, the interface is also sharp in the TM image. So here, we do this kind of the thickness dependent, this kind of superconductivity. And in here, we perform the apex measurement. As I told you, if you want to see this kind of quantum anomalous score, it must be still topological. So here, let's say if it is still topological, we do the in situ apex measurement at room temperature, and we can see the Dirac surface state here, and the Dirac point is really close to the Fermi level. And here, we do this kind here. For the first one, we keep n equal to 20. We keep the thickness of antarite, and systematically change the thickness of chromium-doped bismuth antimaterite. We can see that for 20 unit cell antarite with 1 quintuple layer chromium-doped bismuth antimaterite, you already see this kind of superconductivities. And the TC onset is around 10 Kelvin. The TC naught is around 3 Kelvins. And we further increase M, we can see 2 quintuple layer bismuth antimaterite chromium-doped and 20 unit cell antarite. The TC onset is 10 Kelvin. TC naught is around 7 to 8 Kelvin. And with M is greater than 4, the superconductivity is saturated. And here is the TC onset is around 12 Kelvin, and TC naught is around 10 Kelvins. So here we keep the thickness a 8 quintuple layer bismuth antimaterite and gradually change the thickness of antarite. We can see when the N is less than 18, there is TC onset, but there is no zero resistance. That means the superconducting area is still short range superconducting this kind of the areas. And for A is greater than 20, you will see this kind of the zero resistance, and TC naught is around 10 Kelvins. And here is we demonstrated this kind of the interface-induced superconductivity in the chromium-doped bismuth antimaterite and antarite heterostructures. So here, the chromium-doped bismuth antimaterite is ferromagnetic, and here we realize superconductivity. So we speculate there is coexistence of ferromagnetism and superconductivities. And I can do the transport in my own lab. And here is the RG curve. TC is 12.4 Kelvin. TC naught is 11 Kelvin. We do the Hall resistance measurement at 10 Kelvin. 10 Kelvin is here. Nothing. The Hall resistance is 0. That's reasonable in superconducting state. So at 12 Kelvin is superconducting transition regime. There is a hysteresis loop. At 14 Kelvin is above the TC onset. You see a larger this kind of the hysteresis loop. So based on this kind of transport property, indicates this kind of ferromagnetism and superconductivity coexist in our samples. But here, I talked with my friend Xiaodong Xu from the University of Washington. We do this kind of the RMCD measurement, is optical measurement, to check, for RMCD measurement is only sensitive to this kind of the time reversal symmetry breaking. It's not sensitive to the superconductivities. So here we can see with decreasing this kind of temperature, we see this kind of the hysteresis in all the temperatures. This also further confirms this kind of the coexistence of the ferromagnetism and the superconductivities in our this kind of the chromium-doped bismuth antimer telluride and iron telluride heterostructures. And here, the Vidal from at Rutgers performed this kind of the magnetic force microscopy measurement. And here we can see if you apply the high magnetic field, and if we at 2.2 Kelvin is uniform, this kind of the single domain state is the red color. We systematically increase this kind of magnetic field, this kind of domain will gradually form at the high magnetic field will become the downward this kind of the single domain state. And by analyze this kind of the MFM image, we can get just the contrast of this image, we can get a hysteresis loop. And this kind of hysteresis loop is consistent with the Xiaodong's this kind of the RMCD data. The HC is similar. Here is 2.2, here is 2 kelvins. So here is from the transport from the RMCD and also from MFM, we demonstrated the coexistence of the ferromagnetism and superconductivity in the chromium-doped bismuth antimer telluride and iron telluride heterostructures. So finally, I want to show you that we performed the STM measurement on this kind of the chromium-doped bismuth antimer telluride and iron telluride heterostructures to further confirm the coexistence of the ferromagnetism and superconductivity in the top quantum anomalous core layers. So here, this is the STM image, and we see this kind of island. This is typical, this kind of large-scale STM image, and this atomic resolution. So this is the tellurium atom. There is triangular, this kind of the defects. These defects is just the chromium substitute, this kind of the bismuth and antimony or antimonys in the top of this kind of the chromium-doped bismuth antimer telluride layer. And we systematically change the thickness of the chromium-doped bismuth antimer telluride thickness. For m equal to 1, we see this kind of the proximity-induced gap, and systematically increase the m, symmetrically increase the chromium-doped bismuth antimer telluride, we see the gap decrease. If we fill the gap, we see, the gap, the proximity-induced gap continuously decrease as a function of the m. And from theory prediction, usually thinks the proximity length in ferromagnetic superconductor, this kind of interface is short, but based on our experiment, the proximity length is actually not quite short. It still survives when the thickness of the quantum anomalous core layer is greater than 10 nanometers. So here, that we call it interface-induced superconductor. So here we demonstrated why we call it interface-induced superconductivities. So we grew half layer of 0.5 quintuple layer, half layer of chromium-doped bismuth antimer telluride on this kind of 38 unit cell iron telluride. So here is the half layer. This is still iron telluride. We throw this kind of red arrow to the STS measurement. We see that there is a superconducting gap here, and on the surface of iron telluride, there is no superconducting gap. So that means the superconductivity only appears on the top of the 1 quintuple layer chromium-doped bismuth antimony telluride. So this kind of the data demonstrated here, we call it interface-induced superconductivity in the chromium-doped bismuth antimer telluride and iron telluride heterostructures. Finally, this is I want to, in this talk, I first introduced quantum anomalous core, and later I let quantum anomalous core to join superconductivity game. And why we have this kind of the motivation, the motivation of our project is we really want to use the MBE to synthesize quantum anomalous Hall and superconductor heterostructure with the sharp interface. I definitely agree that STM is a good this kind of the approach to prove the Majorana physics in the quantum anomalous Hall and the superconductor heterostructures. But if we want to apply this kind of the Majorana physics into the real application, we need to fabricate a device. So here, what I want to say is, if we want to detect the Majorana physics in quantum anomalous Hall and entire heterostructures, we need to fabricate the Jocelyn junction device or interferometer device. So here we fabricate this kind of quantum anomalous Hall and nanobeam Jocelyn junctions. We see this kind of the Jocelyn effect. And here is we still doing this kind of the experiment. And hopefully we now be based on the quantum anomalous Hall and the entire heterostructure I just introduced to realize the Majorana physics. And we also can realize this kind of the to fabricate the quantum anomalous Hall and entire this kind of the Mach-Thunder interferometers, if we could see the oscillation as a function of the flux, is the magnetic flux, that should be uncontroversial, this kind of evidence for the the exploration of the Majorana physics. So here, I give a summary of my talk. I introduced the beauty of the MBE. We use MBE to fabricate magnetically doped topological insulator and also magnetically doped topological insulator and entire heterostructures, and to realize this kind of the interesting phenomena. And we, in magnetic TF film and multilayers, we see this kind of quantum anomalous Hall effects. And in quantum anomalous Hall and entire, we realize the interface induced superconductivities. And I just briefly introduce how to detect or probe this kind of chiral Majorana physics in quantum anomalous Hall and entire heterostructures. And finally, I want to thank my students, my postdoc, and also my collaborators, and also thank the agency and the private foundations. With that, thank you.